ladies and gentlemen. My name is Sandberg. I'm manager of Volvo Vehicle Dynamics CE department in Gothenburg, Sweden. And I will talk with you a bit about our experiences, learnings, and strategies when we're using our VI-grade DiM150. So improving, not replacing, what do I mean with that? When we started out investigating the need and the requirements for a driving simulator back in 2011, so almost 8 years ago, or a little more than 8 years ago maybe even, we figured that we needed something to improve our efficiency and the flow in the product development. And that was to meet the improved demands of reducing lead time for the product. Although that is still true, that we have reduced the lead time and we have improved efficiency and flow using the DiM150, actually the major learning is that it has taught us to become better engineers building better cars, which is what I want to talk about today. And to introduce, I will show you a short movie that was recorded last year during the launch of the new Volvo S60, our best driver's cars to date, I would dare to say.
The new Volvo S60 has been designed to be a true driver's car, offering an engaging and enjoyable driving experience in all situations. Advanced chassis technology puts it at the forefront of driving dynamics. This does not only apply to the new S60 itself, but also to how it was developed. Volvo Cars was one of the first car manufacturers in the world to implement a full-scale, state-of-the-art simulator for driving dynamics. The simulator played a vital role in the development of the chassis performance on the new S60.
With this advanced simulator, we have been able to test and evaluate things like wheel suspensions, brakes, and geometry very early in the development process, even before the first test car was actually built.
With the simple push of a button, parts of the wheel suspension can be exchanged, or settings can be modified, and the simulator driver experiences the difference in real time.
We've continued to add functionality to the chassis simulator to enhance the use of it. And we built the brake system rig connected to the chassis simulator and a static simulator that we can use for early testing. The goal is to have an environment where we can evaluate everything that we can also test in a physical car. The 60 series cars are the first where the simulators have been used from the start through the entire development process. And it's really exciting to see the cars out on the road now, knowing that our efforts with the digital cars have made a significant difference.
There are several areas where our work in the simulator has improved the S60 significantly. For example, based on our test results here, the geometry of the rear axle was changed in order to improve the balance and agility. With the simulator, we have an excellent foundation once the real-life testing begins. It's about making the car better, not just save time. I believe we have created the best driver's car so far in Volvo's history.
So that was a quick introduction to what I'm actually going to speak a bit more about now in the following slides. So in 2011, my current manager at the time, Stefan Karlsson, and our technical expert within vehicle dynamic, Egbert Bakker, we started an initiative to better link objective and subjective assessment techniques, and especially to copy the slogan of VI-grade, bridge the gap between testing and simulation. So one important start for this was the implementation of VI-car real-time at Volvo. We wanted to use this as a complement to our more high fidelity but also time consuming modeling and simulation using Adam's car. And that was kind of the kickoff to improve the efficiency of our CE processes. But we also started to create this map that you can see here. There are standing on the 3 pillars of CE simulation, measurements of physical cars on the test track or on a test rig, and subjective rating driving physical cars on the road. But it became quite evident that we were missing one important link. Between CE simulations and objective measurements in the cars, we had our metrics DNA, so basically all the vehicle dynamics metrics that we use to explain how the car is behaving in an objective way. Between the physical measurements and the subjective evaluations of the physical cars, we had our standardized rating forms, starting at a top level and going more and more down into detail until you have a very close link to the actual objective metrics. But in between here, CE simulation and the subjective assessment of the car. What did we need there? I think you know the answer already. Of course, we needed a driving simulator. At that point, we had no experience of driving simulators for vehicle dynamics, but Stefan, my manager, got a chance in 2011, I believe it was, to try VI-grade's current simulator, which was based on the Ansible Motion platform, and already there started to think that this is probably something for Volvo. So we started a long process of understanding our needs, our requirements on the simulator, and how it could be integrated to optimize our development process. And in 2014, eventually, we installed the VI-grade DiM150, as we felt that this is the best simulator for our needs to fulfill our dynamic requirements, our requirements to have a realistic cockpit, so enough payload capacity, and also with a software suite that integrates well with the development process that we already have using Adam's car and car real-time, for example. So this next picture that you've probably seen a lot of times, it's quite widely used, shows the installation from 2014 with a V40 cockpit, so based on an older vehicle model. Since then, we've upgraded to an S90, the model that was released in 2016, spending quite a lot of extra time on properties such as sound insulation and features within the cockpit that have added to the driver immersion. One of them being the active chair and the active seat belt that has helped us greatly in immersing especially novel drive sim drivers. The V40 cockpit, however, was not scrapped. Around this one we built a static simulator, which is the one you see in the picture here. And the main purpose of this one is to prepare for tests, to check the models that we use, but to the same extent we use it for student projects, PhD projects, and introducing new employees to the drive sim environment. And actually by introducing this one, we increased the use of the dynamic simulator as well. And it's a nice environment. We've also tried to connect them to be able to drive head-to-head with 2 simulators, which is a nice feature. A driving simulator is not equivalent to a test vehicle, and we believe that it shouldn't be treated as such. And what do I mean with that? We've learned that an efficient way to use a driving simulator and to convince our testers of its usability is to use it to do what you cannot do in a physical car. And in this way, we remove any conflicts of discussing, okay, which environment should we use in a certain situation? No, we use each environment to its full potential and in the way that it contributes in the best way. And the driving simulator enables some key features that simply isn't possible in a physical car. One of them being zero waiting in tuning. So you have no workshop time, of course, to change settings. I will come back with some details there of how we do that. We have zero time in transportation to test sites and different test tracks and events. And we also have zero personal risk. So what does this give us, really? In the traditional way of testing vehicles, because the time in the workshop is so long for each setup change, we might do a change in the setup, exchange something in the suspension, for example, and then we go out and we do a lot of testing. We do many different driving scenarios. And that is to optimize the testing time in relation to the workshop time. However, using the driving simulator, because changing the setup is so quick, we can turn this around, which has some key benefits. So we can, which is that we can focus on simple scenarios and then do a lot of setup changes for one scenario before we move on to optimizing the next one. And especially for non-experienced or novel drivers, this is very, very useful. And we can do A to B comparison, switching back and forth within the blink of an eye. Also, it opens up for a lot of more experimentation, because you don't need to anticipate what change to do next. You can simply just try something, or you can ask the operator of the drive sim to give you something that you didn't expect. To do blind tests is much more easy in the drive sim. So that is basically a way to add a business value. We do testing in a different way, adding even more value to the development cycle. But we have some more important ways of adding value by using the driving simulator. Probably the most important part so far in our experience is that we can use it to show our colleagues within Volvo in different departments how their input of data matters and how their input of models to use in the driving simulator matters for the behavior in of the car in the end. So you might have an engineer that sits and develops software or hardware, such as tires, and we can invite them and say, okay, this is actually what happens with your data, and this is why it's important. And because of the repeatability of the drive sim environment, it's actually even more powerful than to do so in a real car. We can also show possibilities with models and designs. So if our developers have ideas, it's a very quick way of experimenting with that, of course, compared to ordering a physical part. And last but not least, demonstrate the product content and the product status to important stakeholders, such as higher management, product management. And I will come back to some examples of where that is very important. We also, as I'm into here, we want to add business value in the most efficient way. And we want to reduce complexity as much as possible with the models that we use. So our strategy is to prefer model-in-the-loop simulation before software-in-the-loop simulation, before hardware-in-the-loop simulation. So why is that? Well, this is a very simplified picture, but basically saying that a model-in-the-loop, just representing the software or hardware that we have, is what gives us the most adaptability, so it opens up for experimentation. And the complexity is low, so it's quick to work with. But sometimes the fidelity is not enough, so we might need to actually go towards software in the loop or hardware in the loop. And depending on the status of the project, the availability of models, and the requirements for the test, we will end up in different situations in this chart. but we always prefer model in the loop. With that said, I also wanted to introduce our latest addition to the driving simulator environment, which is our hardware-in-the-loop brake system test rig. So this comprises of the full hydraulic brake system that we have in the car, including the electronic control module, the main cylinder, and all the hydraulic lines, and all the corner modules with the brake calipers. It also has, so this is the actual hardware-in-the-loop setup that we have connected in the drive sim. So here we have bundled together all of the hydraulic parts with the calipers and the electronic control module. And we also have here a linear motor to actuate the main cylinder in the car. So basically replacing the pedal and the foot of the driver. And the reason why we do this is that we simply cannot have a plant model which has a fidelity which is high enough for the very, very high frequent dynamics of the control module with all the hydraulic valves. So there is still a need for hardware in the loop. And now going on to some case studies to showcase what are we actually working with in our driving simulator. The first one relates to changing the axle kinematics of the car. So in this picture, you see what is basically a Simulink interface for our real-time testing, real-time tuning tool that we've developed at Volvo, and which is probably the best addition to the simulator we've done in terms of software since we started. So it basically includes a selected set which replicates the data that we have in car real-time for certain components. In this case, the bump stops here, the suspension strut, and the roll bar. This is the leaf spring of the rear axle on the spa platform. And in this picture also we actually represent the kinematics and compliance of the full suspension corner. So what we can do is that we can add or reduce the gain of the lookup tables in car real-time while driving. So we can change any parameter of the kinematics or the compliance even mid-corner for the driver. And by having a fading function, we can also ensure that he has a smooth experience going from one setup to the other, to the third, to the fourth, etc. So in one lap around the test track, you can test 10 different configurations if you would like to. And in the S60 project, we use this, as you may have remember from the video. Matthias there, he explained how, or mentioned quickly, how the rear axle was tuned to improve the stability and agility of the vehicle. So we found during testing of the first prototypes that the high-speed dynamics of the chassis didn't fulfill our requirements. And we thought that, well, the only way to really treat this is to make a hardpoint update to the car, which is of course cumbersome in the physical vehicle. And also it's difficult to experiment. Maybe if you want to know exactly what you should do, you can make that update and then you validate it. But this was not the case. So by using the real-time tuning tool, we could adjust the locations of the hardpoints in a very quick manner, and in 2 to 3 days, we found a new setup that fulfilled our requirements on the agility and stability of the car. We updated the physical car in the next prototype series and validated that behavior. So it worked very well. In the end, we don't know if it actually saved us time or money, because we didn't intend to delay the project because of this reason, but it certainly gave us a much better car. The second case study relates to battery electric vehicles. One great challenge that we've had is that the center of gravity usually migrates downwards and rearwards when we add the batteries and the electric motors to the car. And for us, that's been quite a great challenge because it means that our cars are 50-50 or even rear weight biased, where most of our cars traditionally have been front weight biased. And we realized quite quickly that we needed to look into how to dimension the tires for this situation. And the original approach, we thought that wasn't really efficient enough. But the challenge to start with was that how do we go from the petrol vehicle to the BEV vehicle? Can we use the same tires? And we figure out quite quickly that no, this is not the case. And I can mention that during the making of this video, tires were harmed. And what we can see is a test of a tire with too much normal force and probably too much lateral force as well, compared to what the tire is actually designed for. And you can see the deformation here of the contact patch if you look closely, that this is a tire in a situation that probably won't give a very high confident feel to the driving experience. It is basically not stiff enough. So should we do this for every tire that we want to experiment with? The traditional approach for simulating tires would be to actually measure each tire that we want to evaluate and create a tire property file for this, which is probably more than 3 sets, to be honest. But this wasn't feasible due to time or cost. So what we did was that we started a collaboration with the Fraunhofer Institute in Germany, evaluating the CD tire model, which is a physically based tire model that allows, as Fraunhofer calls it, morphing of the tire size, or basically changing the width, the height, the aspect ratio of the tire. And thanks to its physical description of the parameters, we can then predict the cornering stiffness behavior, the vertical stiffness, and the damping, and some important parameters. So this basically means that we can measure one single tire, and we can extrapolate within a certain region to the tire sizes that we believe are interesting for the project. So quite quickly, actually, using this method, we found a set of tire sizes for the front and the rear axle that we were confident would give good driving behavior balanced towards efficiency for the car. So we had a new vehicle concept. We had the new challenges for tire selection that was quite different from what we've had before. And new challenges then to secure the handling attribute. And after a while, we were quite confident that we'd reached a good solution. So we took the typical approach. We created some data sets, and we presented this to the product management and said, this is our recommendation based on these curves that you see here. This is curves of critical speed, but you don't need to look at the details there. However, we quite quickly realized that they didn't really understand the importance of what we were trying to tell, because they didn't actually understand the phenomena that we tried to resolve. So what did we do? Of course, we used the driving simulator. So instead of just showing them the objective data, we started out by having our stakeholders doing an A to B comparison in the driving simulator for a stability test case on a highway. And these were non-experienced driving simulator drivers, but I can honestly say that everyone appreciated the difference, and they very well understood what we wanted to say by comparing the non-preferred tire setup with the preferred tire setup. And because they understood that driving situation, we had a much better discussion around the objective data afterwards. So the discussion gave much more value, and we could together take much more informed decisions. And also for ourselves in this case, because the confidence feel and the stability of the vehicle is such a subjective experience, it was essential to actually use the driving simulator to ensure that we recommended the best solution in the end. So even for ourselves, the objective data was not enough. And I would easily say that in this example, the potential cost saving was at least $10 million. So in itself, much more than the investment of the DiM, because of what could have happened if we didn't take the right and correct decisions for tire sizing. That might lead to having to redesign the suspension or the body in a late phase. The third case study focuses a bit on the fact that even though we focus the use of the driving simulator for concept development before we have physical cars, we have found a great benefit also for testing and improving cars that are actually already in production. So in this certain example, we found that, or we thought that we could improve the dynamic behavior, the handling and steering of the car by changing the spring aids, or the bump stops also called, in the suspension. But this is something which is difficult to actually tune in the car. You have to order a set of testing components, which means that you need to make quite educated guesses before you order those parts. And we couldn't really see or understand everything we wanted from objective data. So what we did was that we created a parametric curve that explained the behavior of the bump stops that we could tune in real time in the driving simulator. So we could, in the blink of an eye, change the stiffness, the block length, the progression of the bump stop, and evaluate the steering performance. So eventually we ordered 3 different sets of bump stops to validate in the physical car. And we chose actually one of these directly then to go into production. And this saved us minimum 4 to 8 weeks. And it probably wouldn't have happened if we didn't have the simulator. I think we would have stayed with the old ones because it would have been too cumbersome to even do the project at all. And last but not least, I also want to mention the benefits for research and for our learning. So we don't only use the driving simulator for product development, but these are 4 examples of PhD projects that we have conducted or are about to conduct where the simulator is an important tool. The first one, correlation of objective and subjective assessments, is a project that finished around 2 years ago. And the driving simulator was an essential part because you have a very repetitive environment to do the subjective assessments, and you directly also have all the objective data you would ever need as output from the car real-time model and the motion queuing. So you get a very good significance, statistical significance in all the experiments that you conduct. Second one, co-simulation in virtual verification of vehicles with mechatronic systems, is a project that is ongoing right now. And the focus there is to optimize the co-simulation for mechatronic systems. And the next step is actually to validate some of these developments of models in the driving simulator, and especially for the steering system, which is, because of its stiffness, very challenging to simulate well, as I believe most of you know as well. Then we have 2 projects that are, this first one is just started. The candidate started a few weeks ago, and we have one more project to be started after Christmas. The first one relating to motion sickness for autonomous vehicles. We believe that the driving simulator will be very important, as we can have very precise control of what motions we actually subject the driver to. And quite related to this topic as well is the last product, motion cueing for conceptual and disruptive technology. And the key thing we want to achieve there is to have a more informed way and a more objective way in tuning the motion cueing, so that we can set the motion cueing and know that we can trust it also for vehicle concepts that we currently have no experience from. Which means that we cannot do any comparison to the physical world until many years from now. And with that, I would like to thank you very much for your attention.